Nerding and Hoarding. Quick and dirty DIY electronics. Hello and welcome to Nerding and Hoarding. Today we are starting the build of the quick and dirty vocoder. A vocoder is, or an analog vocoder, is a rather complex circuit to normally. But we are in the business of making things quick and dirty. So we will take a stab at doing this right here. If you don't know what it is, it's sort of kind of an early voice-controlled speech synthesis thing. It takes, you have a microphone where you speak or sing with your voice. And this incoming signal is then passed through a bank of bandpass filters, and possibly there is a high pass filter on the one end and a low pass filter on the other end. And then when this signal is passed, divided into bands, you might say, then this audio signal is transformed into a control voltage using an envelope follower on each of the bands. Then this goes to a voltage controlled amplifier right here, where it controls the incoming signal. So the incoming signal comes usually from a synthesizer keyboard, where you play on at the same time as you sing in a microphone. And this can be a signal that has a lot of harmonics, sort of like a square wave. It is passed through another bandpass bank that has the same values as the previous one. And this is the incoming signal that comes into every VCA. And then all of these signals are summed. So the signal is put together again in a summing amplifier and then outputted. I can explain. So the bandpass bank just uses very simple passive RC filters, meaning that it is 2 resistors and 2 capacitors per band. The envelope follower uses 1 diode, 1 resistor and 1 capacitor, and 1 buffer from an operational amplifier. The voltage controlled amplifiers are just Vactrols, which are an LED shining on a light dependent resistor. And we have some amplification of the incoming signal, amplification of the signal here, and the amplification of the outgoing signal. So in all, I'm hoping that this will fit on a nice little PCB that I will try to design right now. Here is the very quick and dirty and simple circuit. It's not very simple, but I will guide you through it. The voice comes in here and it is amplified using this operational amplifier right here. Then it is divided into 7 bands, as we call it. And if we follow the path of band 1, we will see here is the band pass filter. It's basically a low pass filter, which are these two, connected to a high pass filter, these two right here. Then we come to this is the envelope follower that makes the signal that goes from like this to a voltage. This voltage is then buffered right here. I tried to use it without a buffer, but it didn't work too well. And then this goes to a Vactrol. And this is where this simulation doesn't work anymore. But so this Vactrol here, or this LED, is connected physically to a LDR that is right here. So if you please remember this position right here, and we then go on to the input of the keyboard synthesizer, or as it's called, the carrier signal. So I tried to simulate this using a square wave and a noise signal. So we get a lot of information to filter. Then this is amplified. And you can control the amplification rate with this potentiometer. And then if we follow band 1 right here, goes through exact same value band pass as the voice did. And then here is the resistor, and this resistor is inside of the Vactrol, which is hot wrapped. So the yes, the LED is right here, and this is wrapped in hot shrink plastic. All right, so you understand. If this light goes up, then this resistance goes down. And this value is not correct right here. This will probably need to be a trim pot or something, because this is only here to make the Vactrol into a voltage divider. So in a voltage divider, if you just put a resistance in series with something, you don't actually alter the voltage, you only alter the current, and the current might lead to a voltage drop. But if you have a buffered signal, that's not going to happen. So anyway, so this is not exactly this correct value right here. Anyway, so then it goes to the summing amplifier. So this resistor right here, together with the other 7, or the total 7, are part of the summing amplifier. So all the bands are once again put together and amplified here in an inverting amplifier, and then inverted back again, and then this is put out right here. So exactly this, we will now just make another drawing of this exact setup here, but in another program. And now I have made an image of the simulation right here, and I will just alter it slightly to make it easier for me to make notes on it and so on. So I'm desaturating it and inverting it and changing the contrast right here. So now I will use this to scratch out what I have done. So let's start with adding an input jack right here. Oh, let's call it voice or mic jack. So we got the mic jack. So that will be like this thing right here. Wonder what is actually the problem with my computer now. So I will see if maybe I have to empty the trash can right here. All right. Okay, so now I have, yes, just like that. And yes, please work now. Layers, darken, okay. All right, so now we have the input ready. That's why I draw it like that. I have no idea why it's lagging this bad. Maybe it could be actually because I'm having such a large screen resolution. I will stop this video right here. Or no, I will just keep going. So let's just keep going right here. It's better. All right. So now we need an operational amplifier. And I have a bank of them down here that I often use when I work with this program. Just because it helps me make it easier for myself. So we have the positive on the bottom side in this particular operational amplifier. I mean the non-inverting goes on the down part. And this I have just drawn this, and these are net flags, but they are also the symbol of an operational amplifier. So it helps me tremendously with drawing in EasyEDA, because otherwise you will have to remember what pins to use on the and it looks like this usually, and it's very confusing to work with this, I think. So then we would have connected one thing to here and another thing to there and another thing to this pin right here. But I made these so just one net flag per pin, and the net flags are then, you make a net flag like this, you click here, wire tools, net flag, and then you just copy this. And this point right there is exactly the same point as this point right here, so you don't have to make very long leads everywhere. So it's very helpful for me. You can try it if you want. I won't force you or anything. Yeah. Then we take a potentiometer right here. Okay. And to rotate something in this application, you just press the space bar, which is a very nice feature, I think. So yeah, it's going to copy this right here. So we need one more, just a fixed resistor. And I think I put it right here. There's also a library in this program, but I think it's not very easy to use. So I often just copy the ones that I have, that I know how they work. Because each component is attached to one footprint. So this is a symbol, and the symbol also carries information about the footprint. That when we have drawn the schematic right here, then we press design convert to PCB, and then we get all the footprints. So that is the drawing that will go on the PCB that is sort of the same size as the component itself. And they vary different. They vary. We just can say that they vary in size and in design and all that. So I find it very easy to, or I find it more easy to first have all the components in a special project where I only have my components, and then I copy paste them into here. So now it would have been good to have a value on this one, but we don't have that. So we can just guess maybe. Maybe we should call this pot 1 input level. And why don't we? Let's say, how much do we want to amplify it? Well, let's say that we would go with. Let's say we want to go with 25, or is that too much? Yes, it might be too much, but let's just do like that. Let's call it pot 1. Pot, didn't I call it pot level in? It doesn't want to be called that. Maybe you can't have any pot in level. You can't have any space in that. All right, so let's do it like this, and then just attach this one to here and there, and then finally here. So now we are actually ready with all of these, and we can start with the yeah, this is serious lagging here going on. So, all right, so we can start with actually band. Okay, now I get lost in. So let's start with band 1, even though we could start with the low pass, but let's start with band 1 here, because I think that would be easiest. To just add some text here that just says band 1. So then we need one capacitor and one resistor. I just put them up here for the time being. So let's call this R2, and this is a value of 560, and yeah, that goes in parallel, no, in series, yes, sorry, series. And then we have this one, 1 microfarad going to, so we call this C1. If you name something, you see C1 already exists. So then maybe we should find this C1 and we just delete that one. So then we can try again. Yeah, let's call it CR1 first and then change it back to C1. And we don't get a message saying that it already exists. So then we can go on here. And we put a little ground here, like that. Oh, do you see that? It's not connected. What happened there? What the frick? All right, so, and the value should be 1 UF, like that. So we now have this settled there. And then we put a resistor here called R3, and it has a value. No, wait a minute, that's not right. It's supposed to be here. Yes, and it's supposed to be a value of 1K2. No, wait a minute. Control C, Control V, and then we copy this and paste it here. But I do want it to be called 2 because it makes it easier. So then we have to take this one instead, and Yeah, this is pretty much repetitive right now, because then we will, so I will sort of finish one line here of, or one band, going through the bandpass filter, and then to the next step, which is the envelope follower, and finally the buffer here and the Vactrol. And then we can just copy this and change the values of these, so we don't actually have to draw everything. So it's kind of slow, but still it's kind of okay. And we can also add some text here, if we just do like this. Okay. And we can write what things are. So this is a band pass filter, and this is an envelope follower envelope. So please excuse my spelling, because I am dyslexic. Okay. So we have one diode here, and we will call that D1. And we just connect this. I'm putting some space in between here to show like this is one function, and this is the next function. So we have let's see what we have. 10K going to ground, yes, and we also have, what do we have? We have 10 microfarads going to ground as well. And these just have to be connected like this, and yes. So let's see if we can put some space here. And now we need a buffer, an operational amplifier buffer. And those are quite easy to make. So they are very complex things, but they are easy to work with, I think. So you just connect the input to the one with the plus sign on it, and you connect the minus sign to the output sign, just like this here. So we can call this the maybe the Vactrol or the envelope buffer. Yeah, and let's make it a little bit smaller, just like that, to save some space, like that. And now finally, we can try to draw on this, but it's not working. Nope. All right, we are experiencing some technical difficulties, but we will soon be on our merry way. All right, like that. And then finally, the Vactrol, which looks like this. So I found this in the bank of, or in the library. So you click this button and you get sort of 1 million components. So you have to really search a long while right there, which is why I do it like this. That I don't use that for a day-to-day basis. I just used that once. And if I have a new component that I do not know how to use, then I will. No, if I have a new component and I don't have that, then I have to go to the library and get that. Okay, that's how it is. So just like this, but I think we missed one little thing here. We need to have a little resistor here. I forgot to draw that. So just a small resistor here. And that resistor will be 1K. Okay. Yes, yes. And then this will go to ground. So we now have one line ready here. So what we have to do is just copy this and paste it maybe here, and just make sure that things are connected. Yes. And then we just change the names to make them correctly show what it is. This is now band 2, and we have to just check the values here. And make sure to double check and triple check these values, because they will make all the difference later. Is this correct? Yes. Okay, so that value is correct. 560. That is correct. Okay, here we run into a problem, because this is wrong now. This, when we copied it, didn't automatically change the numbers here, because this needs to be 3 now. So then we just delete this, and we go down here and get the number 3. And very important, remember to change the orientation of the plus and minus signs here, the inverting and the non-inverting input. Then just place that in there and make sure the connections are connected like this. Yes. All right, so then maybe we could actually make a line up here. Well, if we copy all of this, yes, and we put it up here. Sorry, and we remove this. And then we cut this, and then we paste it here as many times as we want to have it, which I don't exactly remember. 1, 2, 3. 1, 2, 3, 4, 5, 6. And also we should have it up here with the low pass only, which is very simple actually. It is only like this. Oh, wait a minute, what happened now? So there's just some confusion about this. And let's see. Yeah, we just have to move around a little bit of the things right here. Then I'll call this band 0, just to confuse things, and I call this the low pass filter, and I just remove the high pass like that, and like so, and we double check up here what are the values. So 1.2k, that we can write 1k too, which is easier to read if we have very, very small writing. And then we see that we have just to paste the operational amplifiers here. And as you see, they're a little bit different because I draw them by hand, or not by hand, by computer, but anyway, you understand what I mean. We could do like this and take them just one at a time, every one that we need. Oh no, I did a copy, that's bad. That's bad, just undo that. And make sure to cut and paste, not copy and paste. And make sure to double check. Alright, so double checking that time right there. Yeah, you see we have to connect this. Yes, that is connected, this is not connected. Connected. You can test if something is connected by moving it around like this. Okay. So the values now, and these are very important to get right. So let's start from the top and we will go through all of them. Alright, so first check the low pass filter. Is it correct? Yes, it's correct. And check band 1, is it correct? 560 and 1.2k, 1.2k, yes. And then band 2 down here, 270 and 560, yes. All these programs work in a different way, so it's a little bit hard to pan around here, yes. All right, so now we know that we have something wrong here. 170, okay, 120 and 270. Okay, and then what do we have? So that is correct already now. All right, so 68 and 120. So what was that? 68 and 120. And I'm using the same values on every capacitor because I have a large bag of these capacitors. So better use them, right? 68, 120, yes. And then 47, 68. All right, double check now. Which band are we on now? We are on, yes, change the number of the bands here. This is, so confusion rate is increasing with the number of copies you make over something. And you must have some kind of method to make sure you don't confuse the numbers. Okay. So now I'm just making a high pass filter down here, and so double check now. 47. No, there's something wrong now. Something is wrong. You see here, I accidentally did something wrong here. So just start again and do everything again. Let's see, 68, 120, and 47, 68, and finally 33. So we already filled this. This A3 here, so we have to make it larger. The paper will have to be larger. Nope. How do you do this? Hello, what's going on? Yes, so we move to A2 size paper. But we're actually making a lot of progress here. We're actually ready with half of the circuit, sort of. Right here, 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 here. And this will just be a copy of this. So it's kind of actually quite good. So let's just copy this right here and paste it over here. No, wait a minute. We have forgotten last operational amplifier. Well, not the last one, but one of the last ones. So, and now we have let's do everything in order now. So this is pretty much a copy of that. So let's copy this. And remember to change the operational amplifier. So just quickly delete these in order not to mess up anything. So, but now we ran out of our operational amplifiers here. We used up 8. So let's see if I have actually made any with numbers over 8. Otherwise we have to do it manually. Oh, unfortunately I haven't done anymore. So let's just do that here. So copy and paste. So this is in my project where I only keep the all the components I use. So let's see here. We will start at 9. So we change the name of everything here. Just add 4 to every number here. Unfortunately, it wants to jump away here, so we have to fix that. Okay. 6 plus 4 is 10. 6 plus 4 is 10. 6 plus 4 is 10. Yes. And 7 plus 4 is 11. 7 plus 4 is 11. 7 plus 4 is 11. So this might actually not make so much sense for you what I'm doing right now, but it's just my method that I will maybe explain in another video, if I am going to make a video about that. So now we changed all of the net flags right here, so now we just have to change them right here as well. 9, 9, 9, 10, 10, 10. I just tried to say quickly that I made this myself by just taking a line here and draw a triangle like this. And then I took the a chip here, quad hop amp, I put it like so, and I take this called net flag, and I put the net flag here on each of these, and then on each of these right there. And you have to change the color here because you can't see it very well now, can you? So, and then I copy this, and I put it in the correct place on this one. So you sort of go from pin. This is more, I would say, sort of a footprint, and this is more practical. Not component, but building block. All right, so where were we? Where were we? Well, we are adding 4 to every number. So 7 plus 4 is 11. 7 plus 4 is 11. 7 plus 4 is 11. Yes. 8 plus 4 is 12. 8 plus 4 is 12. 8 plus 4 is 12. So now I just have to save this, and I will have this available every time I open this project. And then we copy this over to this vocoder here, and let's take the lowest number first, and always cut and paste, never copy and paste from these, and put it here. And this, what do we call this? We call this the wait a minute, I got it, but I forgot it. So what do we call it? We call it the carrier jack. So we have the carrier. Maybe we won't have to amplify that quite as much as we had to amplify the other signal. So these should be correct here all through the line because we just made a copy of this one. But let's look at the image. So what do we have here? All right, so we have the Vactrol coming here. So now we need to find a way for us to be able to have something that is on the same time here. Oh my god, that's slow. Yes, very slow. And at the same time here. And there is where we use a net flag. So we will have to make some net flags first. And we have to call them something that helps us remember what we are doing. So why don't we call this V? So for V for Vactrol, 1 and A. V1A. Yes, V1A. But the good thing, if you are making the numbers in a good way, you get it to count for you, which is kind of good. So maybe we just call it V1. And then the next one should be V2. And then V3, V4, V5, V6, V7, V8. So this is basically just invisible wires. Or actually wires are actually nets in the mind of the computer. So it's, what the fuck are you doing? Sorry for that language, but why do you give me a mail in the middle of my working here? So we have 14 flags here, which is very good to have. Let's clean up here a little bit to make it a little bit less chaotic. Too much information in the same place is not so good. So now we just need to remember here what are our net flags names and on what band are they. You can write a list if you want to, or you can just keep double checking the images. So here we have a little problem, just that there are two texts on top of each other, so I just quickly fix that, and yeah, I mean, this is probably only you're going to look at this, because this is just a schematic, but like this. Now we actually put here the V1 like this, and then and then I said, and then V2 like this. So we say that here is the Vactrol. So text would be very helpful here. The text will say LDR Vactrol, just like this, and we can just copy this and paste it down here, change the numbers, just add 2 like this. Okie dokie. And now we add 4 to every number here, and 4 times. And finally, well, not exactly finally, but sort of finally. So now we add 6 times. No, 6. Yes, 9, 10, 11, 12, 13, 14. All right, and now, so then we have that right there. Now we just need this part right here, and this is the value that I am not that I do not know what to do with. So probably this value will have to be set by experimentation, and the way to do that would be to build one line or one band. So one band from here, I have to build this, and then build this, and this, and this, and then one line over here, this, and this, and see how much does anything change on here. So either that, or we put some trim puts on this, for example, and also here. So that's something I don't actually know how to do it. But one thing we could do is put trim puts in place so that we could use them if we want to, but we don't have to use them. To create the PCB in that way that we make it possible for us to test different things on it. So a way to do that would be to okay, now I have to find a wait a minute, I have to test a little thing now, because I need to know what is okay, what does this component, what footprint does it have? And I'm not so sure about that, so I just paste it here. Fortunately it's invisible like this, and then I have to save this just because that's how the project works. So test 55, and then design, convert to PCB. Now keep going, and now I get to see how the pinout is. So this is what it looks like, and this is a 9mm pot only. I know that I somewhere have made a pinout that is that has both this pinout and the trim pot pinout inside the same pinout, which would be very helpful to have right here. So if I paste these, no, I didn't want to go. So copy these two right here. One is called 1 and one is called V. No, one is called 15. Yes, copy, delete, paste, and then file, save, design, convert to PCB. Now keep going, and there you go. Both of these have both, so that's really good. So I can use either of these if I wanted to. I'm not so sure about that now, but let's just do it anyway. Let's test it out. Sorry about that sound. All right, so where were we? Yes, we are going to use not this, no, delete that, but we will use something. Let's see, where were we? Yes, so maybe in 2 positions we will have these. So they do look like this, both of them. So we should be able to, if we call them like this. So, and if we connect them like this, so here comes the signal from the Vactrol, and it goes both to the trimmer, and also we add a normal fixed resistor right there. Then we will get something looking like this. And this, what can it be? It might be 100, and we will have, just to add a little text here. So test trim slash resistor, and then like this and like this. So if you see here, it would be possible to have the circuit totally without these connected. The signal will still come here because the trimmer will only decrease the strength of the signal. And it can also be possible to have both these, or one of them, or none of them at all. So I think if we do this, we are able to, when we get the printed circuit board, we can actually test straight on it. Okay. So then we just have the output amplifier, or the summing amplifier. And then, yeah, all right, so we have a fixed resistor right here. And we put this here only so that not too much will come from here, for example, here and in to here, and messing up things here. Instead, yeah, so it will be like this. Yes, very good. Just copy this. Bum, 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 and finally, bummily bum. Oh my god, how many components are we actually at? This is so exciting, isn't it? So let's see if we could actually rotate this. Yes, we can. Portrait update. So allow me to just make a little cleaning up here. Just like this here. I'm just moving around things. Nothing is actually happening here. So I just want some a little bit larger titles here. Okay, so this will be a little bit larger. How do you make something a little bit larger? Well, you press right here and you take a large. So this is the voice part. And this is the, what do we call this? The synth part. Synth part. It's just for me to understand a little bit more what's going on. There we go. And then we're just going to sum these up with a summing amplifier. A summing amplifier is an inverting amplifier because an inverting amplifier is having one thing connected to ground, and that will help with something. I don't remember what exactly, but it's a good thing to have when you're summing something up. And how does a summing amplifier look like? Well, it looks like this. It looks like this. So we take two operational amplifiers here. So why don't we take number 10 and number 11? Because they are the next to come up, I would say. So cut and paste. And then we just try to get it to look like the other thing that I did. So look at the other image. How does the other image look? Well, it looks like this. Both the positive non-inverting inputs are going to ground. So just take a ground. And no. First, we have to make sure that we have the same orientation. Look here. The non-inverting is down and the non-inverting is up here. So we have to do like this. This is something that will maybe quite often make something not work. Control V. No, it didn't work. All right. So Control C, Control V. Yes. So we got that down, which means we did it. So I believe this could have been maybe 500 or something. So let's see what we could. Well, we could use this like that. I'm just, let's see here. Isn't this supposed to have a value? Yes, of course it's supposed to have a value. And the value is supposed to be 500k, like that. And double check. Otherwise, we go from here to here, and then to here to here, and finally to there. And on this side, it goes like this and there. And then it's having a 100k potential, no, a fixed resistor like this, and like this. So just wire these up, like this, and like this, and this, and this, and this. And finally, like, like this and this, into the inverting input, you see, into inverting. And then we just have an output jack. Well, first a little current limiting resistor for safety measures, so that we don't short circuit anything. If we accidentally put this to a ground, then it will just put 100 ohms there and burn out this one right here. So now, final thing is take an output jack here. Just copy the carrier jack. It doesn't want to do that. Hello, please. All right, copy and copy and paste. And just sort of rotate to make it look good. And yeah, we might want to get it to actually fit inside the paper. So I'm just going to try to do that by doing something. All right. Oh, this is irritating. Sort of irritating. Delete node. Delete node. All right. I don't have time to delete nodes all day. Please focus. All right, I am focused. It is the computer who is not focused. Yes, I know. All right. So this one goes down here, and we call this the output out jack. And as always, I don't exactly know how to connect these because I never learned that. But sort of like this. Why doesn't that work now? All right. So like that, we got our out jack, and we got it sort of. We're done here. We have one operational amplifier left here, so we could just include it down here, and then we have to take all of the ICs here and move them into the bottom here and line them up nice and neat. Yes, and there's the power connector as well, so that we get power coming in. And just remove everything that we're not using. So down here, this is the power connector, and then we have to connect. Powers are connected here as this thing, which is sort of the net flag for the power. So we have to connect those to here, and now we can also attach some some capacitors to help out with stabilizing the voltage for each of these if we want to. I'm not sure about when you actually need that and when you don't need it. So what we could actually do is, let's see, if we do something like this. Let's see, I'm trying to think here, that's why I'm talking so strange. I'm just saying, what if we, what? Excuse me. No, let's just skip that and do just like this instead. No. I went to the ground there. Could have said ground, yes, like that. So now we could add a, if we copy a capacitor here, and we maybe put it here, like this. So let's see, no. So we're a little bit tight here, let's make some more space before we try to go on here. Or you know what, let's just do it the other way around, which is like this. Oh, please, how hard can it fucking be? Alright, so it's seriously messing with me right now, so I'm just gonna put it up here and let's instead take, no, okay, yes, like this. I put this here, so now we have some kind of voltage stabilization going on here, but it should probably be smaller, maybe like, why not 150 nanos, that is, nanos. Yes, that could be good. So let's just copy this for each of the things right here. So as I said, I'm not exactly sure about how to do this, so please, teach me in the comments fields below. When do I need capacitors, and what values do I want to have for stabilizing the voltage of the operational amplifiers? Anyway, I do it like this. It looks ugly, but it will do the trick. If you want to, you can do it like this. Looks a little bit better. Okay. We can see if we can find a use for this. Otherwise, we will just probably connect it to ground. I'm not sure if we have to do that, but why not? Why not? It just doesn't do anything. I think that is. It will only compare ground to ground and put out the difference into ground itself. So we say that we are done, and we design, and we press convert to PCB, and then we click no, keep going. Nerding and Hoarding. Quick and dirty DIY electronics.